So for section 9.4, we're moving on to geometric sequences in series. So the first thing, goal for the day, define and identify geometric sequences. Then we're going to write explicit formulas for geometric sequences. And then finally, we're going to evaluate geometric series. Starting off with a definition. So a geometric sequence is a sequence in which there is a constant ratio constant ratio between consecutive terms. We've talked about constant ratios before, and in those, or the time where we talked about constant ratios were for exponential functions, so this is very comparable to an exponential function. So some examples, maybe you've got a sub n equals 2 to the nth power. So the n is the exponent. Or maybe it's a sub n equals 17 times 43 to the n minus 1 power. Yikes, it's a little messier, but it's an exponential, well, sorry, it's a geometric sequence. It'll help us find the terms of a geometric sequence, I should say. So taking a look at these four examples, what I'd like you to do is take a moment, see if you can identify whether you think they're geometric or arithmetic. Kind of remembering the definition for arithmetic sequence is consecutive difference or constant differences between consecutive terms. Or maybe it's neither. There is one of these that is neither. So take a second, see if you can identify whether you think it's arithmetic or geometric. And if you think it's arithmetic or geometric, maybe tell me what the change is. All right, whether you pause or not, let's move on. So taking a look at this first one. This first one is, in fact, arithmetic. To prove that it is, let's identify the constant difference. Constant difference is -7. It's going down by 7. 100 minus 7 is 93. 93 minus 7 is 86. 86 minus 7 is 79, etc., etc., etc. Okay, next up. 180, 90, 60, 15. Let's see, it's divide by 2. Divide by 3 over 2, divide by 4, doesn't seem geometric. Subtract 90, subtract 30, subtract 45. Doesn't seem to be arithmetic either. That is neither. The third one, that goes 5, 1, 0.2, 0.04. That is geometric. And for constant ratio, for constant difference for arithmetic, we use D. For ratios for geometric, we're going to use the letter R. It's 1/5. We're dividing by 5 every time, or multiplying by 1/5 every time, or if you want to think about it as a decimal, 0.02. Last one, 1/4, 1/12, 1/36, 1 over 108. That is also geometric, where the ratio is 1/3. Thinking about it as you're dividing by 3 every time, and remember, just kind of like with exponential, we want to describe it as what you're multiplying by every time. So we're multiplying by 1/3. Taking a look at the formula that we use for a geometric sequence, so to find the nth term, a sub n, of a geometric sequence, it's a sub n equals a sub 1 times r to the n minus 1 power. Remember, a sub 1 is your first term, r is the common ratio. So what you're multiplying by over and over and over and over. Taking a look at this pattern here, we got 3, 12, 48, 192. Thinking about the formula we're using, a sub n equals a sub 1 times r to the n minus 1. Well, we need to know what a sub 1 is. Well, it's our first term. It's given to us. It's 3. R, our ratio. What are we multiplying by every time? So to get from 3 to 12, 12 to 48, 48 to 192, we're multiplying by 4 every time. So we're using the formula a sub n equals 3 times 4 to the n minus 1 power. Now, I like to put that in parentheses. You don't have to, but I think it's a little cleaner. Now, we're asked to find the 7th term of that geometric series. So we got a sub n equals 3 times 4 to the 7 minus 1 power. Cleaning that up a little bit. Oop, I made a typo. That should not be a sub n anymore. That's a sub 7. So a sub 7 is 3 times 4 to the 7 minus 1, or 3 times 4 to the 6th power. 3 times 4 to the 6th power. I'm going to go out on a limb and say many of us don't know what 4 to the 6th is off the top of our heads. We can use a calculator in that. We got 3 times 4 to the 6th gives us 12,288. So we can say final answer, a sub 7 equals 12,288. For the second one on this page, we got 0.001, 0.01, 0.1, 1, 10. Using that same formula, we need to know a sub 1 and our r. A sub 1 is the first term in that list, 0.001. R, what are we multiplying by every time? We're multiplying by 10 every time. So plugging that into our formula, we got a sub n equals first term 0.001 or 0.001 times 10 to the n minus 1 power. Find the seventh term. A sub 7 is 0.001 times 10 to the 7 minus 1 again. So we got a sub 7 equals 0.001 times 10 to the 6th power. Now thinking about some patterns you might know about multiplying by things with 10 or 10 raised to an exponent. If we got 0.001, one trick I know a lot of people have learned is if you're multiplying by 10 to the positive 6, take the decimal place, move it 6 spaces to the right. 1, 2, 3, 4, 5, sorry, counting and talking at the same time. Not the easiest thing for me right now. Fill in some zeros. So if our new decimal place is over here, then the final answer would just be 1,000. So we got a sub 7 equals 1,000.